Okay, so today we are going to cover solving exponential equations. And we're going to add we've done this a little bit already, but we're going to add some new skills and some new methods to solve them. So far, we've been solving equations of the form, let's say we've got 3 to the x is equal to 16. Okay? If we had this kind of an equation, what we've been doing so far is converting this exponential equation into a logarithm equation by switching our input and output. So we'd say, okay, instead of 3 to the x equals 16, we're going to say log base 3 of 16 is equal to x. All right, so we would just convert this exponential equation into a logarithmic equation. And now this would be the answer. Log base 3 of 16 is the answer for what x is. And if we wanted to put that into a numerical answer, like an approximate numerical answer, we would just throw this into a graphic calculator and see what it spits out. It's going to be approximately, 2.5, somewhere around there. All right? So this is step 1, is knowing that we can just convert an exponential equation into a logarithmic equation and go from there. Now, that works great when we've only got x on one side, we've got a fairly simple exponential equation, and so there's not a lot of moving parts, right? And we can even do that if we get more complicated exponential equations, like let's say we had 3 times 4 to the x plus 1 equals 49. Let's say we had something like this, okay? At first glance, there's a lot more going on, but really, when we break it down, there's an exponential here, and there's some, other numbers around it that we can manipulate we can strip those away. It equals a number, all right? So we can do what we need to do with this to get it into the form of the other one we were just looking at. So we can say, okay, let's subtract 1 from both sides. That's easy. So that gives me 3 times 4 to the x plus 1 is equal to 48 now, all right? Now we're going to divide by 3. Okay, so this gives us 4 to the x plus 1 is equal to 16. Now from here, it's in the exact same form as what we were just looking at. So we're going to convert this exponential into a logarithm. That's going to say we're going to go log 4 of 16 equals, when we take the input there, x plus 1. All right, now, log 4 of 16, we know that that's 2, right? 4 times 4, so 4 squared is 16. So this is 2 equals x plus 1. Subtract 1 from both sides, and we get x equals 1 for our answer. Okay, so that would be how we would solve an equation like this. And again, we're not really doing too much beyond kind of algebra 1 level manipulation to get the exponential on its own, and then convert the exponential equation into a logarithmic equation. Right? But what we're going to run into is types of equations where we can't actually do that. We're going to get types of equations where we've got exponentials on both sides, or we've got variables on both sides. So let's suppose we had 3 to the power of 2x was equal to 3 to the power of, let's say, x plus 4. Okay. Now what we're trying to figure out is, all right, I've got 2 exponentials equal to each other. So I can't just try and convert this into a logarithmic equation because I have 2 different exponential equations. Which one would I convert? If I try to convert this one, I say, okay, so I'll convert this into a logarithm. That'd be log base 3 of, what is this? 3 to the x plus 4 equals 2x. All right. I mean, yeah, we could go from here, and we could apply our power rule to pull that out and try to solve for x. But there's an easier way with this one here, right? There's a much easier way. And we'll show you how that works here in 1 second. So the first thing I want to think about is, all right, what are these two things saying? What is this equation telling me? This side of the equation is saying I've got 3 multiplied by itself 2x times. So this is going to be 3 times 3 times 3, times 3. That's a total of 2x times. And on this side of the equation, that's going to be equal to, this is 3 multiplied by itself, x plus 4 times. So 3 times 3 times 3 times 3. And this is going to be a total of x plus 4 times. Okay? So if I've got over here 2x, 3 times 3 times 3, and over here I've got x plus 4, 3 times 3 times 3. The only way that those two things are going to be equal is if 2x is equal to x plus 4. All right, so we can go ahead and say, oh, this is obviously going to be that 2x is equal to x plus 4. And maybe it's not obvious to you. Sorry, I shouldn't use that word. But if you're seeing it now for the first time, and maybe it hasn't clicked in yet, but think of this as a collection of things being multiplied together. If I've got two collections of things being multiplied together, the number of things have to be equal to each other. Right? I can't have 4 3's multiplied together over here and 5 3's multiplied together over here and have those two things be equal. So the only way that they're equal is if the number of things are the same on both sides. Okay, so here we've got 2x things, here we've got x plus 4 things. All right, so then 2x needs to equal x plus 4. So then we just solve that. We get 2x is equal to x plus 4 minus x, and that gives us x equals 4 for our answer. Okay, so this is kind of a logicking our way out of dealing with an exponential way of dealing with this. We just say, okay, so if these two things are equal, then the exponents obviously have to be equal. There's that obviously word again. I'll try to cut that out of my vocabulary. But that's the idea behind this way of solving the equation. And it works. As long as the bases are equal, we can do that. We can just say, all right, if these bases are equal, we can just strip away the exponent and solve it for the exponents. Okay? Now, let's suppose we didn't recognize that. Let's suppose instead we're like, ugh, I don't know. I mean, I've got 3 to the 2x over here, 3 to the x plus 4. I don't know what to do with this. Well, here's the thing that we can do anytime we get an exponential equation and we want to get rid of the exponential. We want to get these exponents out of there. All right, let's suppose, to make it a little bit more difficult, instead of having the same base, we've got different bases. Okay? The trick that we can do here, okay, the thing we can do here is we can just go ahead and take the logarithm of both sides. All right, now think about this for a second here. If I've got two things that are equal to each other, the logarithm is a function. All right, so as long as the input is the same, then the output's going to be the same. So if I take the logarithm of this and compare it to the logarithm of this, because those two things are equal, their logarithms will also be equal. So we're going to go ahead and we're going to take the logarithm, and we can choose any base for this step. I'm going to choose base 3 because it's going to match with this 3. I could also choose base 9 to match with this one, but you usually want to use the lower one. You'll see why. But we're going to go ahead and choose log base 3. Now this will work with any log base. You can do it with any base, but it makes your world a little bit easier if you choose the correct base. So log base 3 of 3 to the 2x. Now notice we're not converting our exponential equation into a logarithmic equation. That's not what we're doing right now. That's what we did before. We converted this into a logarithmic equation. Instead, what we're doing is we are taking the logarithm of both sides. It's a slightly different method, okay? That's going to be equal to, and again, log base 3, because we can't change the base. If we're going to take, if we're going to take log base 3 of this side, it's got to be log base 3 of this side as well. Whatever we do to one side, we have to do the exact same thing to the other side. So that's going to be 9 to the x plus 4. Okay. From here, what we want to do is we want to apply our power rule. Okay? If we remember the power rule of logarithms, that tells us that log of a to the power of b is equal to b times log a, right? We can strip the exponents out of the logarithm. That's the idea of the power rule. As we take those exponents, we yank them out. Don't get them anymore. Okay, so down here, if we apply the power rule, what that lets us do is take this 2x out and take this x plus 4 out. Okay, and they become multipliers. So we get 2x times log base 3 of 3 is equal to x plus 4 times log base 3 of 9. All right. Now what we've got here is a linear equation, right? Log base 3 of 3 is a number. All right. It happens to be 1 in this case, but if it was something else, it wouldn't matter. Log base something, a log with no variables is just a number. A log with no variables is just a number. So we can treat this just like any other number. Okay, we can add it, we can subtract it, we can multiply it, we can divide it. All right, and that's what we're going to do here. But first, we're going to simplify these as much as we can because I don't like having to write log base 3 of 3. I'm lazy. I'm going to say that's 1. I'm just going to rewrite that as 1. That is 1. And this one over here, log base 3 of 9, I'm not going to write that a ton of times either. That's 2. I'm going to write that as 2. Okay? Now we're just going to rewrite this. We get 2x times 1, so that's 2x, is equal to x plus 4 times 2. All right. Now, what does that give us? That's why you pre-test your examples, because you're going to see something pretty messy here. But all right, so we're going to multiply that 2 in here. So we get 2x is equal to 2 times x is 2x. 2 times 4 is 8. 2x equals 2x plus 8. Uh-oh. Well, we can see what's going on here. Subtract 2x from both sides. We get 0 equals 8. What that tells us then is that there's no solution for this problem. All right, and that's what I'm saying, like, I should check really before I start doing these to make sure it's going to work. 0 equals 8, so there is no solution to this one. But let's suppose, I got something else, I would solve for x like we did, right? This is just algebra 1 stuff right here, right? This is a linear equation. We can solve these without any trouble. But these are the steps that we would take to solve an exponential equation where we've got exponents on both sides with variables on both sides, okay? So let's go ahead and write down the steps. Step 1 is going to be take the log of both sides. Okay? And we want to choose the base for the logarithm that matches the smallest base on the exponents that we're dealing with, right? So here, the smallest base was 3, so we want to do log base 3. But, that's not necessary. We can still solve it even if we had a different base, just by using our logarithm rules. That just makes our life easier. All right? So base of log should be equal to the base of the exponent. Okay, so that's step 1. Take the log of both sides. The base of the logarithm should be the base of the exponent. If there's multiple, choose the smaller one. Step 2 is going to be to apply the power rule. Power rule again tells us that if I'm taking the logarithm of an exponent, I can take the exponent out and get it as a constant multiple instead, as a multiple instead. Not a constant multiple necessarily, it could be a variable, but as a multiple. So I take the exponent and turn it into a multiplier instead. Step 3. And actually, we're going to call this step 2a, is going to be to simplify. Simplify. And really, this simplifying step, we should be doing that constantly when we're dealing with logarithms. Anytime we can eliminate a logarithm completely, turn it into a whole number, yeah, that's good for us. All right. Like I said, mathematicians, me especially, we're lazy. We don't want to write log base 3 of 3 when we could just write 1. We don't want to write log base 3 of 9 when I can just write 2. All right. Now, if I got log 3 of 8, well, that's going to be 1.8765309. And I don't want to have to write that out. So I'm going to keep that as log 3 of 8 if that's what I have. But if it's a whole number, if it's something that's going to go nicely, there we go, easy. Okay, so step 2a, simplify. Step 3, solve for x, okay? And then of course step 4, which should be, I guess, step 3a again, is to simplify again. All right. Now, step 3, solve for x, right? Wow, why don't you just draw the whole owl for me right there? So I know this is kind of saying a lot with very little, the solve for x part, but once we apply the power rule, usually we're going to wind up having a linear equation, right? A linear equation is what we solve in Algebra 1. So we should be able to do step 3. It's going to be familiar to us once we recognize that, you know, a logarithm is just a number when it's already got its inputs put in for us. So these are the steps that we're going to take to solve exponential equations. All right, and there's going to be a problem set for you here in class. The bell work will be related to this, and then what we're doing in class today will be related to this. So that's what we're going to be working on today. Yeah. If you have any questions, of course, let me know, but we're going to go forward with this.